So we're going to look at an application of the definite integral. Before we do that, let's talk just for a second. What does the derivative tell us about a function? What is the derivative? Tells us the slope of a function. Okay, what does the definite integral tell us about a function? Tells us something about area, right? So the derivative gives us a rate, and the definite integral gives us an accumulation. Okay? So in physics, you have a formula: distance equals velocity times time. Okay, d equals rt. Usually it's rate times time, but velocity. Remember, velocity is actually a rate, which is the derivative of position. Okay, so velocity is the derivative of position. You're okay with that? And we know that if we integrate velocity, we actually get position. Right? So the derivative of position is velocity. If we integrate velocity, we get position. Okay? So putting this idea together, when we integrate a steady velocity of 30 miles per hour with a lower limit of t equals 0 and upper limit of t equals 3, we get the integral from 0 to 3 of 30 dt. And this will actually give us the total distance traveled over those 3 hours. Let's evaluate the definite integral above by graphing the function and then finding the area under the curve. So let's graph our function. Now what are our t values that we're going to be looking at? 0 and 3. So we're integrated from 0 to 3, so 0, and then I'll come over here and put 3. And then what are the y values we're going to be looking at? In other words, what is the y value at 0? And what is that, according to this? Our function is 30. Think about, what does the graph of 30 look like? Okay, it's a straight line. How else would you describe? Not just straight like this. A horizontal line at what y value? 30. So if I'm going to label my axes, I've got a t-axis and a velocity axis, right? V of t. And our velocity is a constant 30. And so if we graph this function, it's just nice and horizontal. We're just going to 3. So we're actually going to be finding the area of what shape? A rectangle. So the integral from 0 to 3 of 30 dt will be, well, the base of this rectangle is 3, and the height is 30. And so we get 90. And it says it's the total distance, so based on the units, 90 what? So what would be the distance? 90 miles. Okay. Now let's use the physics formula. Distance equals rate times time. Okay, now what was our velocity for this problem? 30. And what's our time? 3. So our distance would be 90 miles. Now think about this for a second. What are the units on the velocity axis? What are the units? So miles per hour. And what are the units on the time axis? Hours. So when we find the area of this rectangle, we're multiplying miles per hour by hours. And so what are the units left over? Miles. Okay. So the area under the curve, aka the definite integral, actually gives us the amount of distance that we've traveled. Okay? In general, if r of t is a rate at which something is produced, in this case, what's being produced? What can we say is being produced? Yeah, as we're driving along, there's some length being produced, right? So there's this length, this imaginary line behind us that's measuring how far we've traveled, right, a distance. So if r of t is the rate at which that distance is produced, velocity is that rate, or the rate at which something happens. So let's say mushrooms grow at a certain rate, so we have a function, between t1 and t2, then the accumulated total of that something, so in this case the total distance we travel, if it's mushrooms growing, the total amount of mushrooms or whatever, is the definite integral from t1 to t2 of our rate. Okay? So the integral of rate, the definite integral of rate, gives us the amount of change. Okay? So it says, suppose the car is proceeding along at a variable speed, meaning not just 30 miles an hour, but it's actually changing speeds as you drive. the formula d equals v of t cannot be used to produce the answer of how far the car travels in this case, because in the formula it's assumed that v is constant. It's assumed that you're driving, you set cruise control, and you're just driving. That's how d equals vt works. However, we can find the actual distance using calculus, specifically the definite integral. So it says, suppose the velocity of a car is v of t equals 40 minus 20t miles per hour. Use the evaluation of a definite integral to find the total distance traveled between t equals 1 and t equals 2. Graph the function to find the area under the curve to produce the answer. So let's start by graphing our function. Now, what are the times that we're going to be looking at here? Okay, just 1 and 2, right? T equals 1 and t equals 2. Now, 40 minus 20t, what kind of function is this? It's just a linear function. And so we know it's a straight line, so all we really need are endpoints. Right, so we don't need to plug in a whole bunch of numbers. We need to plug in 1, we need to plug in 2. So when we plug in 1, what are we going to get? We get 20, so I'm going to definitely go up on my y-axis to 20, or my v of t axis, I guess. My v of t and t. And when we plug in 2, what do we get? 0. So my highest value on here is 20, my lowest is 0. When t is 1, we get 20. When t is 2, we get 0. And so we're finding the area bounded by t equals 1, t equals 2, and our function in the x-axis, or in this case the t-axis. So we've got the area of a triangle. So the integral from 1 to 2 of 40 minus 20t dt is equal to a half. Now the base here is 1, and the height is 20. So half times 1 times 20 gives us the total distance traveled of 10 miles. Now notice how, again, the physics formula would work just fine if we were driving at 20 miles per hour the whole time. Right? It would work perfectly fine. But here, how fast are we going at an hour and 5 minutes? Are we going 20 miles an hour? Are we going 10 miles an hour? Are we going someplace in between 20 and 0, right? So we're actually able to calculate the exact distance even without calculating an exact velocity at any given time. Okay. Now notice in this example, the velocity never became negative on the interval specified. So what does that mean if the velocity didn't become negative? Yeah, so they didn't change directions, right? It's just we're driving forward the whole time. So in example 4, the velocity will become negative, which means the car is reverse directions. The meaning of the definite integral now means the displacement of the car and not the total distance traveled. Okay. So since we're going forwards and then backwards, this is going to tell us displacement. What does displacement mean? Kind of. It tells us position related to where we started. Okay, so how far we are from where we began, essentially. Okay. So it says, suppose the velocity of a car is same velocity formula. Use the evaluation of a definite integral to find the displacement between t equals 1 and t equals 4. So we're going to find how far from where the car was at t equals 1 does he end up at t equals 4. That's what we're going to be doing. So let's start by graphing our function. Now this time, what are our t values that we're looking at? 1 and 4. Do we need to plug in a million different numbers? Which numbers do we want to plug in? 1 and 4. So we plug in 1, what do we get? So we get 20. And we plug in 4, what do we get? Negative something, yeah. Negative 40. So I'm going to come up on my y-axis to 20, and then down here I'm going to go all the way down to negative 40. Now I'm not really concerned with scale here. I just want to represent the figure as accurately as I can, but I'm not super concerned with scale. So at 1 we get 20. At 4 we get negative 40. And this is another linear function, so we know it's just a nice straight line in between. And so it's bounded by t equals 1 and t equals 4. And so what do we have here? We have a triangle? We have 2 triangles. And what are we going to do with these 2 triangles? Do we find the area all at once? Okay, we find 2 different areas and subtract them. So what other value do we need that's not already on our picture? Okay, so we need the x-intercept, and that would be where? 2. So how do we get that, by the way? Okay, so we basically say 40 minus 20t equals 0. Solve this for t. It might be more complex in some cases. In this case, it's fairly straightforward too. So the definite integral from 1 to 4 of 40 minus 20t dt is equal to, now for our first triangle, we have a half times 2 times 20. Have we seen that before? Yeah, we actually already calculated that in the previous example, right? So we already knew that was 10. We didn't have to do that again, but it's an example, so I will. Minus, because we're below the x-axis now, 1/2 times, now the base of the second triangle is the difference between 2 and 4. That's 2. And the height, oh, you're right, it should be 1, huh? Here, back up there. Should be 1. So it's not the same as what we did earlier. Sorry about that.
It is the same, but just
Oh, yeah, okay, yeah. Okay. Yeah. Thank you. So 1/2 times 2 times, and then our height of the second triangle is 40. Right? Yay. Okay. So we've got our 10, which we already had, minus half of 2 is 1 times 40, so we get 40. So we have negative 30 miles. Now, how the heck do we get negative 30 miles? What does that mean? Okay. So he's behind where he started, or where he was at time 1. Right? So he's 30 miles behind where he was at time 1. Okay? And believe it or not, that's it. So what we're doing here again, what we're really doing is we're putting context to the definite integral. We haven't gotten any more complex than linear functions, semicircles, okay? We're just putting a little bit of context to what we're doing. Okay? Are there any questions on these 4 examples? Any problems or no?